Okay, if you've looked ahead into the handouts a bit, you realize this one, it starts to get ugly mathematically. And it does, but this is stuff you're smart enough for. You can do it. We're going to do calculations related to time dilation and length dilation. And first we're going to explain why, and you'll see the development of the equations, and we'll practice a few times, and you'll see it's not so bad. But here we go. This is why. This is a quick explanation of time dilation, and I'll give you a longer one.
Two spaceships are traveling together through the galaxy at close to the speed of light. Mounted on one ship is a laser that can fire pulses of light, and on the other, a mirror. The pilot of the first ship fires a pulse at the mirror and watches as it is reflected back. A clock on board measures how long the round trip takes. But now suppose that he does this as the ships are passing an observer on a nearby asteroid. According to relativity theory, this observer sees the pulse moving through space at exactly the same speed that the pilot does, namely the speed of light. But he also sees the pulse traveling a longer distance, because from his perspective, he must add the forward motion of the ships to the motion of the pulse between them. So he measures a longer time interval for this round trip than the pilot does, because he's watching the pulse go farther without going any faster. This effect is called time dilation. If two observers are moving with respect to one another, each perceives that the other's time is flowing more slowly.
Okay, and this is a thing. So you might want to go back and watch that again after, because I'm going to go through the math of that and what that implies with calculating the difference in time, right? How if you're moving, time is going slower for you than if you're staying still. Well, you don't notice it going slower. Your time is going slower relative to someone staying still. Anyway, so let's just do the math. So here we have the Columbia and the Enterprise, and let's say there are two ships, and they're both traveling quite fast. 90. That notation you should get used to. It just means 0.9 c is 90% the speed of light. So if you're going to calculate it, it'd be 0.9 times 3 times 10 to the 8 meters per second. Okay, so TS is what we're going to call the time. Like say you're on the Columbia, and it's the time you measure it to go straight down, and say again there's a mirror right there to shoot it back up again, but we don't really need that for now for this calculation. So what this is saying is, and ds then would be the distance, like the vertical distance between them. Now, in the time it took that light to travel down the Enterprise and the Columbia, but you know the idea that the light left here, it actually landed over here, right? Because it was moving sideways. And again, we're putting this in perspective to our stationary observer, which is Kirk standing on the side, right? On our asteroid or whatever, relatively staying still. So he's right here. What he sees is the light follow this. Now, M, E, and S, I took that from the notation from a textbook, so you have to get used to that. Well, E is Enterprise, actually. I didn't take that from a textbook. But S is like if you were on the ships. M is the measured by our observer, which is Kirk. So he sees this distance. If you were on the ships, you would see the light traveling this distance, right? And then, you know, DE just is just how far the Enterprise has traveled since the light left. Okay? So, right angle triangle, by the way, it's got to mean Pythagorean theorem, which is coming. So, just, you know, calculating some things. Distance, these are all constant speed situations. There's no acceleration. So, the distance, again, from the perspective of someone on the ship, this distance is equal to the speed of light times, because distance equals speed times time, the time for it to travel down. And what I'm really trying to get here is an equation. I'm looking for an equation for time, comparing time according to Kirk, staying still, and time according to whoever's on the ship moving. Okay, so S, like the TM is going to be the time observed by someone staying still, and S is time observed by someone who's actually moving with the light. Okay, so just using distance, speed, time, dE is going to equal to the speed of the ship, which in this case was 0.9 times c, times the time it takes from Kirk's perspective, because Kirk sees this motion, right? The guy on the ship doesn't see this motion. And then dm equals the speed of light, because it's the light traveling this way, times the time, again according to Kirk, because Kirk's the only one who sees it move this way. The guy on the ship sees it go straight down. So if I was going to use Pythagorean theorem on this, right, that would be this equation, right? That's the hypotenuse, the two adjacent and opposite sides. And instead of dm, I'll write ctm. And again, I'm looking to get an equation for what Kirk sees. Get tm by itself, okay? So you don't need to develop this, but you could do it. You're more than smart enough to do it. If you had this equation and had to get tm by itself, that's all I'm asking. That's all I do here, okay? So you're smart enough for this, but you just don't have to. You don't have to be smart enough, even though you are. So you can follow the steps through, but here's the equation. The time that Kirk experiences is equal to speed of light times the time that someone on the spaceship experiences divided by this. Now, there's actually a more standard form that gets used. Sort of factor the c out of it, and then it cancels. And that's how you get this equation here. And this is actually the equation that gets used. And this expression actually has a symbol, and that's supposed to be a gamma. So gamma is the symbol for 1 minus v squared over c squared. So this is, I don't actually use this because then I have to remember what this is. This is the equation. This is the one that's got to go on your formula sheet. And so let me remind you what this is. Tm is time according to someone standing still. Ts is time according to someone in motion. V is how fast that motion is, and then c is the speed of light. So to use that equation then, we say, okay, Kirk, he sees the Enterprise fly at that, so that's V. He's resting, okay, and if 1 hour passes on the Enterprise, that's Ts, because the Enterprise is what's moving, how much time will Kirk? And so if Kirk sits there for, in 1 hour, if he was on the ship compared to if he was on Andorra. And so we're going to say he's on Andorra, which of course is a planet, in the show, not in real life. But he's sitting there. He's the M, okay? We want to know how much time passes for Kirk. The time on the ship is 1 hour, and the speed of the ship. So you just use this equation, pretty straightforward. Sub in, you'll notice the C's cancel, you don't even have to use them, and it's 5.3 hours. So that means that if Spock is on the Enterprise for 1 hour, moving at 0.9 times the speed of light, in that 1 hour, while Spock ages 1 hour, his life grows by 1 hour, Kirk ages 5 hours. He experiences 5 hours, his body ages, his heart beats enough time for 5 hours, while Spock on the Enterprise, his heart beat only the number of times it would beat in 1 hour. So Kirk's getting older there on the planet, which, when you think about it, Kirk always did the land missions. So he was significantly aging himself by doing that. Okay. So some evidence that that has been experienced with time dilation that gives, like, scientists 100%, it's not in question. It's not like, are you sure it's not him just making it up or whatever? Like, no, it is not in question. One of them is just by looking at different particles that would, they can predict how long a particle, you know how there's half-lives of like carbon, like atoms? right, of different types of material. Like carbon has a half-life, I can't remember, 30,500 years, something they use carbon dating. Well, same idea. Any particle has a time at which it will decay. And physicists always observe this. And so depending on how fast the particle's moving, the half-life changes. And it changes. Oh, there you go. Someone's on the phone. It changes. Yay, Mr. Estel got it. It changes exactly according to Einstein's formula. And then the other one, it's pretty cool, is like there's two. We're not going to get too much into the effect of gravitational fields on time, but it affects time as well. So there's two factors. But when they first put put satellites out into space, I've probably told you this before. When they first put satellites out into space, they started finding that the satellite's time was getting off of the Earth time. And of course the satellites have atomic clocks, and they're very accurate clocks is what it is. And they were used for things like GPS. They're finding the average GPS was off by about, I think it was 12 kilometers per day. Every day it would get off, right? And they would have to reset. And it was because they weren't being calibrated to travel at high speed and away from Earth's gravitational field. There's two effects, but we're only talking about one right now. But because they didn't use Einstein's formulas for time dilation, the clocks didn't work. As soon as they programmed the clocks according to the speed they were traveling, and again, the distance from Earth's center, then everything worked out perfectly, right? It's a great piece of evidence. Neat thing, by the way, just a little atomic clock information that you would have, that one of my ex-students, he's in I think now he's in 4th year university at Western. He took it, he was, actually I think he's in engineering now, but he was originally in physics. And he actually got a job working in the physics department, and he went to India and worked on their space program, because they're just working on a space program right now, and he worked on the atomic clocks that were going to be going on their space. I don't know what they were sending up to space, actually, probably just a probe or something like that. But anyway, a little fun physics Huskies connection. So, you know, there's lots of reasons why things can't go faster than speed of light, but I always think a nice, easy explanation is this: is that if you take this equation, okay, the gamma, right, and we assume it to be true, that's our postulate. This is this thing that you can use this for time dilation to calculate time. So you'd have Ts up here, and you know you're looking for Tm. Well, if something was actually going faster than the speed of light, then you'd have a number, you'd have like something over, like it'd be something bigger than 1, right? This would end up being something bigger than 1. And then 1 minus something bigger than 1 is a minus number, which is a negative number under your square root, which you may or may not have learned in math class means it's imaginary, what's imaginary time? So there's tons. There's several, physics can give you several scientific explanations, but this is a nice easy one that falls right out of time dilation calculation. Faster than the speed of light just doesn't work. Okay, so to sum it up then, if two observers are moving with respect to one another, each thinks the other's time is moving more slowly. But this leads to an awesome thing called the twin paradox. And the twin paradox says that you have Alice and Bob, and they're twins, same age. Alice is getting on she's going on a spaceship that's going to be going near the speed of light. And she leaves Earth and comes back 26 years later, according to Bob, who stayed on Earth. Now, if you did the calculations, right, Bob would be like the Tm, she'd be the Ts. And if Bob calculates his Tm is 26, you can calculate that she ages 4 years against Bob's 26 years in that time, right? So if you calculated her Ts, right, using Tm as 26. But there is a however here. The however is that really what the postulate says is that, from Bob's perspective, Alice is moving. But really from Alice's perspective, it's Bob moving. From her perspective, she's on this spaceship staying still, and Bob's moving. Earth and Bob are moving away. So why is it that every scientific piece of evidence says that it's it's Bob who ages 26 and her that only 4. If this is true, right? If this is true, Einstein says it's true. And, you know, it confused me. And it's actually called the twin paradox, but I didn't even know that. But I was at the Perimeter Institute, and I had to run up to one of the physicists and say, can you explain to me why is it that it's Bob who ages 26 years? And the reason is non-inertial reference frames. For Alice to get going on that spaceship, she had to accelerate away from Bob, and that's why. So it's actually, but this is actually called the twin paradox. It's a common thing. Anyway, so we could use the same methodology with the distances the light travels, and you get another calculation, which is that m is, again, somebody looking at the length of let's say the length of a spaceship from Earth. S is if you're on the spaceship and you took a meter stick on the spaceship and measured out how wide the spaceship was as you're moving at some speed v. And what this actually says is that if you're observing, what you observe is actually less than what it is. So something that's moving by really fast will look more narrow than it actually is. It's called length contraction. So as something moves, right? Because if I took this number is always going to be less than 1. So say the length of the spaceship was 100 meters, and then this was 0.8. Then if you're on the ground, you would think the spaceship's 80 meters wide. That's how it would appear. Oh, and there you go. There's the calculation. So spaceship traveling 0.87 c, that's your v. It says, what is the proper length? By the way, proper length means the LS. That's the actual, like, I'm on the spaceship. What do I measure? That's proper length. So if you see that terminology, that's all it means. So I'm on Earth, and it looks like it's 48 meters wide to me. But what is it actually? It's actually 97 if you use the calculation. So there's the implication. A moving clock runs slow, and a moving object appears short or skinny. So, you're the aging supermodel, and you don't want to, if you move really fast, your time will go slower, so you won't age as much, and you'll appear thinner. So it's like the best of both worlds if you're an aging supermodel. Okay, just another quick little bit here.
Imagine 2 observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees 2 bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear, but her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
Crazy, eh? Again, you might want to watch that again to get your head around it, because it's kind of weird and confusing. Okay, yeah, gobbledygook for Kelvin. Okay, so thought experiments. So one of the things I assess you on in this unit is thought experiments, and you have 3 that I give you. one that you make up your own, and then the fifth called it thought experiment, but it's not. It's actually me asking your opinion on something. But you'll get to that in your notes and in the video. So you can work on them as you go. You could do the thought experiment that's coming up on the next page right away. Yeah, it's funny. Okay, so here's the first thought experiment. I might have asked you this one before. I try to avoid using it because I know I use it in the grade 12 course. But so you're in a boat, everything's calm, there's an anchor in the boat, you drop the anchor and it sinks to the bottom of the lake. Does the level of the lake rise, fall, or stay the same? So obviously this has nothing to do with modern physics. Well, I guess everything's to do with modern physics, but the reason why I'm doing thought experiments, of course, is because that's what Einstein did. His first thought experiment, well, probably not his first, but his first, the famous, is he tried to picture what it would look like riding a beam of light. Okay? And that led to the special theory of relativity. Was that train of thought got him to the special theory of relativity. So, you know, I don't want to insult anybody, but, you know, you're not going to be doing ones like that. But I try to give ones that are sort of just common experience that you can sort of wrap your head around, come up with an answer. I think on the next page I have, yeah, sort of what I'm looking for. It doesn't have to be that dramatic, but give me a couple paragraphs or something like that, using at least a little bit of science, not just your gut, right? A little bit of science, a little bit of stuff, physics, or maybe if it's not directly related to something we talked about in class, something in your life you talked about, right? And you know, draw it, make it nice, and then later on you'll write your own. Okay, so this is part of that's going to be the second assignment as part of this unit. And that's it for today.